My name is Tearlach Magri. I am from Malta and attending the University of Malta. And today I will be presenting to you my study titled Unified Load Balancing Strategies for Enhanced Cloud Computing Solutions, which I developed in collaboration with my supervisor, Dr. Rebecca Camilleri. Here is a quick overview of today's presentation. I will begin with an introduction and the motivation behind this research, followed by the specific problem it addresses and the objectives set. I will then move into a summary of relevant literature and explain the methodology used. And I will also focus on the design of the hybrid algorithm I developed, followed by the results and evaluation. And lastly, I will finish with the key contributions, limitations, future research directions, and finally, the overall conclusion. Essentially, cloud load balancing is the process of distributing workloads across various computing resources to ensure optimal performance. It manages incoming network traffic by directing it efficiently across multiple servers, networks, or any other resource. And this approach not only improves responsiveness and scalability, but also enhances system reliability by reducing the risk of service disruptions. This is all typically managed by a software component that resides between the client devices and the backend servers. And as client requests are received, the load balancer balances them to the most suitable server. Now, this decision is made using algorithms that considers multiple factors such as server load, geographical distance, and other potentially performance metrics. And this intelligent distribution helps to maintain efficiency and responsiveness across the system. Now, achieving optimal load balancing is a significant challenge in cloud computing, as this is often costly and inefficient when some servers are overloaded while others are underloaded. And this not only degrades the performance, but also results in higher operational and maintenance costs, especially at larger scale environments. Another major challenge is that cloud environments are highly heterogeneous, meaning that the servers vary in capacity and capabilities. And task scheduling under these conditions is what we call NP-hard, meaning it's computationally intensive to find an optimal solution in real time. Now looking at the current algorithms in use, most tend to focus heavily on performance, such as minimizing response time, but they often neglect resource efficiency, like keeping all servers properly loaded. And this gap forms the foundation for my research. Therefore, the core aim of this research was to develop a more efficient load distribution strategy by combining features from multiple existing load balancing algorithms. And the intention was to leverage the unique strengths of these different algorithms and improve the resource utilization and overall system performance. To achieve this, the study set out three main objectives. The first was to investigate and analyze current load balancing techniques. Second, to design a hybrid model that integrates the most effective features from these selected algorithms. And finally, to evaluate this hybrid approach through simulation and compare its performance against traditional methods using key performance metrics such as response time and processing efficiency. Traditional algorithms include round robin, which is a very popular one and distributes requests sequentially across servers. Another popular one is least connections, which directs traffic to the server with the fewest active connections. Then there is IP hash, which constantly maps a client's IP address to a specific server. And beyond these more advanced algorithms, such as Ant Colony Optimisation and genetic algorithm, have emerged, for which in the next slides I will explore them in more detail. So for the Ant Colony Optimisation, this is a type of algorithm inspired by real ant behavior, whereby ants deposit pheromones on the ground to mark different routes. And this approach combines this pheromone intensity and other information to guide ants towards neighboring nodes. It also has a feature where the pheromone intensity is reduced over time, and this is used to prevent premature convergence. Genetic algorithm is a general purpose search strategy and works with a population of solutions which are improved iteratively through recombination and selection. For representation, the problem variables are encoded as genes in chromosomes, and these are evaluated based on fitness representing profit or utility to optimize. And this search strategy mimics the natural selection by favoring chromosomes with higher fitness for the next generation, and over successive generations, this evolves towards the best solution. Now this slide outlines the core of my proposed solution, a hybrid algorithm that combines Ant Colony Optimisation and a genetic algorithm for cloud load balancing. Firstly, the Ant Colony Optimisation is used for quick local search. It assigns tasks, so user requests, to virtual machines based on simulated pheromone trails, similar to how ants find efficient paths to foods. And this allows for fast and adaptive task mapping. Then genetic algorithm is introduced, which uses evolutionary principles like selection, crossover, and mutation to help explore a wider solution space and refine the ACO-generated mappings. And the key idea here is integration. So ACO and colony optimization generates a strong initial population, and then genetic algorithm is used to improve it further, optimizing for both response time and resource utilization. And by combining these two techniques, the algorithm avoids getting stuck into local optima and responds well to dynamic cloud conditions. It gives us the best of both worlds. So the Ant Colony Optimisation speed and genetic algorithms global optimization capabilities. And this results in a more balanced, scalable, and efficient approach to cloud load balancing. To obtain the results for this hybrid algorithm, I configured CloudAnalyst, which is a cloud simulator, and I simulated a wide range of test scenarios with varying the number of virtual machines and data centers. For each algorithm, I selected and tuned key parameters and then ran multiple simulation iterations to mitigate variability. I then recorded the metrics for the overall response time and the data center processing time. and averaged the outcomes to ensure statistical significance. To evaluate the hybrid approach, I tested it under both low and high workload conditions. These scenarios reflect typical fluctuations in cloud usage. And as can be seen, under low workload, the hybrid and colony optimization and genetic algorithm achieved around 13% lower response times compared to traditional round robin, and also significantly better results than the other algorithms. And under high workload, it still held up really well, outperforming the round robin by around 15%, and again achieving great results against the others. Now, this consistency under stress and under different workloads demonstrates that the algorithms' adaptability and robustness in dynamic environments, and also to validate that the improvements weren't just random fluctuations. I also conducted a statistical test, a one-tailed to sample t-test, comparing the hybrid approach against the next best method, in this case, the Ant Colony Optimisation algorithm as a standalone algorithm. And the results show the p-value below 0.05 at a 95% confidence level. So confirming that the improvements in response time is statistically significant and unlikely due to chance. Now, this work contributes on both theoretical and practical levels. From a theoretical perspective, it introduces a novel hybrid load balancing algorithm that combines two meta-heuristics that haven't been deeply integrated in this way for this purpose in prior research. On the practical side, it demonstrates that the hybrid method can significantly improve response times, load distribution, and overall resource utilization, even under different cloud conditions. And these improvements can benefit cloud providers by lowering operational costs and enhancing the service quality. And also by promoting multi-objective optimization, this study aligns with the current needs in cloud environments, especially for applications that are latency sensitive or resource intensive. Like any other research, this study has its limitations. The first limitation is that all the testing was conducted in a simulated environment. And while simulations allow controlled and repeatable testing, they cannot fully replicate the complexity of real-world cloud deployments. The second limitation is that the algorithm focuses on quality of service metrics like response time and utilization, but does not yet incorporate factors like energy efficiency, fairness, or scheduling overhead. So for future work, several directions are promising. The first one is the possibility of deploying the algorithm in a real-world cloud platform for validation. The second one is extending the algorithm for containerized and edge environments. And lastly, is to include other objectives like cost, energy, and fairness to make the algorithm more comprehensive and adaptable to different scenarios. To conclude, this research demonstrates that a hybrid approach, specifically Ant Colony optimization and genetic algorithm, can significantly enhance load balancing in cloud computing environments. It successfully addresses the limitations of traditional and single objective algorithms by offering a robust adaptive solution that improves both response times and resource utilization. And the results I presented show that hybrid meta-heuristics can play a vital role in modern cloud orchestration, especially as workloads become more diverse and dynamic. And ultimately, this work lays the groundwork for intelligent multi-objective schedulers in the next generation cloud systems. Systems that need to be not just fast, but also efficient and also scalable and responsive to the real world demands. These are the references and the end. So if you have any questions, I can answer them.